Hello, hello. It's on. All right, I think it should be good. Okay. All right, so I'm David Hollinger. I'm a PhD student in the Auburn Lab. For those of you who were able to see Joe Ferguson's presentation, I really enjoyed it. He mentioned how he's really excited to see AI being applied to biomedical engineering and technology. So hopefully that was a good preview of what applications can be done with machine learning. And so today I'm going to talk about machine learning for biomechanics and whether you're going to be using machine learning in your own research or your future job, or you might be working with someone else who might be using machine learning. The goal of today is for you to learn some of the language that it speaks, and then that way you can communicate it well. You can know what machine learning can do, what it can't do, and a few other cool things. And like Dr. Zvala mentioned, there's an extra sub-assignment for this lecture. It's pretty easy questions. If you just listen and follow along, it should be an easy free points. So I just want to start with my research journey. So I was born in the late 1900s, and I went to George Mason University for my undergrad. This is my research supervisor, Nelson Cortez. We focused on lower limb biomechanics, specifically looking at how someone's altered gait patterns might increase the chances of someone having knee osteoarthritis. And after that, I did learning how to do the clicker. I did my master's in biomedical engineering at Stevens Institute of Technology, where we worked on the upper limb, how we can accelerate motor learning for stroke patients using virtual reality. And after that, I did some work full-time at Michigan State University in the medical school. We looked at chronic low back pain, how doctors treating for the SI joint could reduce pain of the low back, but also how we can find biomechanical parameters that would also correspond to a reduction in low back pain. So that was a really good opportunity where I was able to collaborate with people in the medical school and kind of got to see how engineers and medical clinicians operate. And while I was there in Michigan, I also worked for a startup called AvidHeart, where they used these wearable devices to measure your heart health. And this was the very first time where I saw the power of machine learning being used for societal impact. So I was thinking, wow, this is really cool. So let me see if I can apply this to my background in biomechanics in such a way. So I decided to apply for a PhD at Auburn University, where now I can couple these together. And it's been a great experience. So far, I'm in my second year, and we're applying machine learning to exoskeleton technology for Army soldiers. And then also this summer, I'm going to be working at the Nike Sports Research Lab, applying machine learning for biomechanics, physiology assessments, performance improvement. So this is a really good domain where it can cover many parts of research. So yeah. So today what we're going to cover what is machine learning, some of the problems that you may encounter. So like I was saying, the purpose is for you to be able to see a problem and ask yourself, can machine learning be applied to this problem? We're going to look at types of machine learning, supervised learning, unsupervised learning, transfer learning, reinforcement learning, and deep learning. And then we're going to look at some examples in biomechanics, because I feel like there's a great opportunity to marry machine learning with biomechanics. We're also going to talk about limitations and challenges in machine learning, because there are many of those. And then we're going to talk about some tools and resources you can use, so that way later on, if you wanted to apply this yourself, you can have some starting tool or resource to get you going. So any questions before we get started? All right, feel free to interrupt me at any point if you have a question. If something doesn't make sense, I'd be happy to pause and continue. So we're going to demystify what machine learning is. We really need to kind of clear up what it is. And so we have to see why we are interested in machine learning. So the first reason from a general standpoint is that it's relevant. There was a an article from the World Economic Forum that said 58 million jobs are projected in 2022 that are coming out of machine learning. And then there's also lots of opportunities for startups. So I mentioned Avatar as well, but a lot of machine learning applications you can learn on your own, essentially, and then just apply to whatever kind of problem that you have. So it's really useful for startups if you like the entrepreneurial side of research. Every 2 days, we create as much information as we did from the dawn of civilization up until 2003. That was by Eric Schmidt from Google. He's a former Google CEO. This is important because if we have so much data, we need some sort of pipeline that can make meaning out of the data that we have available. With the pervasiveness of wearable sensors and devices, mobile devices, laptops, we generate so much data, and we can use machine learning as a way to make useful innovations. Some other reasons: it's challenging and it's cool. I find it very interesting. So hopefully you'll find it interesting too later on as we go through this lecture. And this was an article I saw just recently came out. There's a $2 million investment to create AI initiative at Auburn. So whether it's happening worldwide or in the US or at Auburn, you're going to run across people who do research in AI. And I feel like it's really important for us to just kind of know some of the basics of AI and machine learning, what it is, what it can do, what it can't do. AI is considered the new electricity. It's going to be good for automating tasks in many different sectors, like I was saying. It could be from manufacturing, logistics, retail, healthcare applications, engineering applications. And so this is going to really transform the way the market is run and the amount of things that we can leverage. So hopefully in the next couple of years, you guys can be prepared when this unfolds and develops. Also, AI has a value creation predicted by McKinsey and Company of $13 trillion by 2030. So that's a lot of money. And you can see healthcare systems right here is about $267 billion of value. So this is a really big transformation of how our society is going to run. So a good definition of machine learning is providing computers the ability to learn without being explicitly programmed. So this was said by Arthur Samuel in 1959, which was a really good definition, in my opinion, from back then, because it still holds true today. And if you have any questions of what machine learning is, keep reverting back to this definition. This is a really good definition. I also like this definition. Machine learning is turning things or data into numbers and finding patterns in those numbers. So it's, for the most part, it's just finding patterns when you have a lot of data. And then also, this fits into the context of software 2.0. This is a world where machines are going to generate code for you. So Google's already developing a platform where you just type in, give me a function that takes the sum of X and Y, and it'll generate code for you. And so this is going to transform how programming operates, where traditional programming, you're in this programming space and you do a particular task in software 1.0, but then what machine learning will do is it'll have an optimization of generating code for you, and it'll be much more efficient, much more fast. So I thought that's pretty interesting. So, okay, so how is this different than just traditional programming? Because everyone here's taken a MATLAB course, right? Okay. So that is a form of traditional programming. So I like to think of this as a food analogy, because I like food. So, so traditional programming is where you take your inputs. Say you wanted to make a grilled cheese sandwich. You have your bread, your cheese. I like pepper jack cheese, by the way. That's my favorite. And then you have your materials, and then you give it rules. So you have a slice of cheese, you preheat the skillet, you cook for a couple minutes, and then you output the objective, so making a grilled cheese sandwich. So that's what a traditional programming workflow is, right? But what machine learning algorithm looks like is you start with the inputs and then you also have the objective, so the grilled cheese sandwich, and instead it gives you the rules. So it'll tell you this recipe of how to make it. If you just start with the inputs and you start with the output objectives, it'll give you the rules. So the reason why we want to do machine learning, well, a good reason is why not, but a better reason would be for a complex problem, you think of all the rules, right? So on the previous example, it was pretty simple. You have a grilled cheese sandwich and it's not too many rules, but for a very complex problem that you have, you guys learned a variety of muscles, bones, and how they all connect with each other in some way. Human biomechanics is really complex, right? So if you can use machine learning to take advantage of learning all the rules, it can be very beneficial to what you're trying to do. So when to use machine learning? So here's a good rule. If you can build a simple rules-based system that doesn't require machine learning, you want to do that. This is the rule number 1 of Google's machine learning handbook, mainly because you don't want to apply machine learning to every possible problem. So a rule-based system is just like your simple if statements in MATLAB, for instance. If it's pretty simple, if there's only a couple rules, you want to keep the rule-based system. But if it's too complex, you want to do machine learning. So here's a hint. This might be a homework question right here. And then I like this principle, Occam's razor. Whenever possible, choose the simplest answer to the problem. So a lot of times people try to overcomplicate things, but if you just keep the design simple, your approach really simple, that's the more advantageous way of doing things, in my opinion. All right, so we're going to talk about some categories of machine learning. We're going to talk about supervised learning, unsupervised learning, transfer learning, reinforcement learning, and deep learning. So these are 5 different categories. Deep learning actually applies to everything here. But some people might ask, why is deep learning being performed today? And so I like to draw this diagram whenever someone asks why deep learning is being applied to today. So I just have a simple XY graph. You have the amounts of data on the x-axis here, and then you have performance on the y-axis. And traditionally, machine learning, it would give you a certain amount of performance, but as the growth of data that has been supplied through, like I was saying, like mobile devices or wearable devices, through time has occurred, there's kind of a bottleneck for machine learning here for performance. However, deep learning, and we'll get to in a sec what exactly that is, but deep learning, it's able to lift the performance even higher and go up to here. We have, we'll say, a small neural network. So the neural network is a type of deep learning, by the way. And then there's even a more lift of performance as you increase the size of your neural network. So if you have a large neural network, it increases even more. So this is kind of the core reasoning behind shifting from machine learning all the way up to deep learning and neural networks. But like I was saying before, you might not need machine learning in your problem. You might not even need deep learning. It depends on a lot of factors. It depends on the amount of data that you have and the problem you're trying to solve, right? Any questions before we continue? So supervised learning. So supervised learning is kind of like that grilled cheese example I showed you, where you have your inputs and your answers, right? So your inputs is what's called training inputs. So it's learning based off of the inputs that are given to it. And it's trying to find the relationship between the inputs and labels just means the answers, right? So this is your cooked grilled cheese. The inputs is your supplies. And the algorithm here in the middle, that's the rules that it learns. So eventually, when you deploy the model onto unseen data, you're able to make predictions on those unseen data. And that's the whole goal of supervised learning. It's mapping inputs to outputs so that way it can generalize on unseen data. And so an example of this in biomechanics is some of the studies we've done in the Auburn lab, where we have wearable sensors like EMG signals, motion capture markers. These are inputs. And say our goal is to find the knee angles here, just purely from our EMG signals. We would map our inputs to our outputs using machine learning. So I've been able to do this over the past couple of years with an accuracy within 1 degree root mean squared error for knee, ankle, hip. So it's a very powerful method, mainly because you don't want to have to use motion capture to measure someone's joint angles. You have a convenient wearable sensor, right? Not everyone can afford all of the expensive equipment, and this is a good way to utilize the power of machine learning using EMG for informative applications like trying to predict someone's knee angles or joint angles. So to reiterate, supervised learning, this learns a model to map inputs to outputs. So say you have a model here with EMG as your input and you're trying to figure out the knee angles. This would be an example of a regression problem. So this is predicting a number, right? So if you are predicting your knee angles, you can have a knee flexion angle of 10 degrees, 20 degrees, 20.1 degrees. You're predicting a number, so that's a regression problem. So if you were predicting a category, that would be classification. So an example of that would be having EMG as your inputs, and you're predicting the categories of walking, running, jumping. These are categories of information. There's not a numerical value attached to this. So depending on your problem, you might be looking at like a risk assessment tool. If someone's at a high risk or low risk of injury, that would be classification. If you are interested in the quantifiable number you want to predict, that would be a regression. So a little question here for everyone. Is predicting the daily stress stimulus using a wearable sensor, would that be a regression or a classification problem? Regression, yes, that is correct. You're predicting a number, right? So you guys solved that by hand, but wouldn't it be nice to just have a wearable sensor that can collect that for you and then you just calculate it on your iPhone or something? So, yeah, so a regression problem. Okay, so we're going to talk about transfer learning. So traditional machine learning, you take one data set to perform a single task, but then for a secondary task, you need another data set. And so it can be kind of inefficient where you need multiple data sets to perform all these different tasks. And it can be very laborious if you build all these models from scratch. So what transfer learning does, it takes the data set from one task, it uses that knowledge to be incorporated into a different task. So that way you don't have to build the new model from scratch. You can use previous knowledge for this application. So example is people here probably taken statics and dynamics. So when you guys had that problem, I think when they're balancing the child on their foot, that problem, that's a statics problem. So otherwise it's a projectile problem, so we don't want that. But that's a statics problem. So you use what you learned from statics and you transferred it for that problem. You didn't have to look at that problem and then go back to your statics class and learn everything from scratch just to do that problem. That'd be very inefficient. So in the same way, transfer learning is the same concept. And this is what Tesla's self-driving car uses. They use some of the state-of-the-art deep learning models as their core, and they transfer that into their pipeline. So all they have to do is kind of change the output predictions and maybe some of the input parameters. So this is going to be a very commonly used approach in the future. You'll see a lot of transfer learning in your jobs. So we talked about supervised learning and transfer learning. That's when your answers are already given. But what if you don't have the final answers, right? What if you just have a lot of data and you're trying to figure out what to do with that? That's where unsupervised learning comes into play. So this is useful when you don't have access to those answers. Examples could be clustering, anomaly detection, or like spam detection, for example. Here's a figure from one of my recent papers that I submitted from a deep learning project I did, where they had a data set of 22 individuals, 11 with injured patients and 11 without injuries. The problem was in their data set, they didn't say who was injured, who was not. So what we did was we used a clustering approach where we used unsupervised learning, and we were able to find 2 distinct clusters, and we surmised that those were the injured group and that was the uninjured group too. But we also followed up with the authors just to double check with that, and so we found that was the case. So that was pretty cool. So you might have a problem where you have a group of people and you don't know what the differences are. You want to just see if there are differences. Maybe you have a group of basketball players and you want to see their movement mechanics, and you don't know what might be different. So you might use a clustering technique through unsupervised learning. All right, we'll take a mini quiz. This is ungraded, so it's okay if you get it wrong. But hopefully this will be a supervised learning approach to these quiz problems that you can learn too. So regression or classification. So remember, this is mapping X to Y. So if you have an image file of a hand X-ray and you wanted to predict the age of the person, would that be regression or classification?
Regression, because they're looking for specific.
Yep, regression because it's a number. And then say you have a video file and you're determining years of experience. Regression, yep. And then you have data from a gymnast-worn IMU sensor, and you want to determine the routine, say they're doing the bolts or uneven bars, balance beam, core exercise. Classification. It's hard to hear you guys, sorry. You guys can speak up. All right, so now supervised or unsupervised. So you want to determine children with crouch gait, so these are people with cerebral palsy. They exhibit distinct characteristics that fall into one of 5 subcategories. What would that be? What was that? Sorry.
Supervised because you already know the characteristics.
They exhibit distinct characteristics. That's good, but you're not quite sure which of the 5 categories they fall under. So that would be unsupervised. But I could see it being supervised actually. If you were given, I guess if you were given more of a detailed report of the individual and then you know those characteristics. But if you were to predict on a new patient, for instance, that comes into your clinic, you would want to use the unsupervised version. That way they can be clustered out into the group that's more similar to what you had. Yes.
Said on the previous slide about clustering, you have to know what you're trying to, like what maybe what to plot and try to look for those clusters. You have to know maybe what you're looking for in the first place. And in doing so, I guess, what happens if you don't know what you're looking for? And you're trying, do you just start randomly plotting different things and seeing if they cluster correctly?
Yeah, it takes a combination of things, and that's why having domain experience is important too. Because, for instance, in our case, we used a k-means clustering approach, and you start out with setting a parameter that tells the model how many clusters do you want to form. So we a priori use that knowledge of putting in 2 clusters, try to find 2 clusters. So it creates clusters and it tries to maximize the distance from other clusters, as well as minimize the distance from those particular data points, so like the subjects, into their own clusters. And so the how well your unsupervised learning model does is how far apart those clusters are, as well as how grouped together the individual clusters are to themselves. So that's another good check. But if you're not quite sure, if you think it's a range of, you could test out a couple. A really important mantra is to experiment a lot of models and just see what changes could happen. So, but yeah, having domain expertise in a certain area can be really useful too. So that's unsupervised. Next, we're going to talk about reinforcement learning. So this is learning a decision from experience. So you are given a reward if the goal state is obtained. This is probably one of my favorite types of learning, in my opinion. This occurs when the ground truth answer is not known, but only if we succeed or fail. So Many of you probably have used reinforcement learning in your own way of living. So as a baby, if you're learning to walk, there's a lot of trial and error. There's a lot of falls. Dr. Zwala has a 2-year-old, and there's a lot of falls among him. So you learn from that experience. And so you start out with an agent. It explores in the environment, and based off of the reward that you assign it to, it either learns or tries something else, essentially. So there's a really good balance between exploration and what's called exploitation. So if you're in Auburn and you wanted to optimize for eating your favorite food, you might just say, okay, I'm going to go to my favorite restaurant today. You're optimizing for that reward. That would be optimizing for exploitation, right? But if you were to explore to a new place in the hopes of beating out that restaurant, that would be more emphasizing exploration. So there's a constant tug of war between exploration and exploitation among reinforcement learning. I think it's really cool. It's used a lot in robots and really cool stuff. So OpenSim had a reinforcement learn to run challenge. Since there's so many parameters, so many muscles that can be shown from the human body, it starts out with 0 experience. So their experience is just falling over. And then you can see it learns a little bit, but takes a dive and falls. But eventually, as you give it enough time, it'll eventually learn to run. So this is cool because you can accelerate the learning process. It won't take, a year, 2 years, 3 years like humans do to learn to run. You can do a simulation and speed that process up. Also, simulations are useful because you don't have to use up resources. So if you were to use this on an actual robot, you might have to go through a lot of your budget to replace the damages of your robot. But if you were to start with the simulation, that could be pretty cool too, because then you can know some of the values you are incorporating into it. And so here's an example of a robot that learns to move. Here, this one is bio-inspired by tendon-driven connection. So it doesn't just explore randomly. It's within a constraint of how a human joint would move. But it does the initial exploration, kind of like motor battling, where babies learn to pull and move their muscles. And so the reward here is the amount of distance to move the treadmill in that locomotion pattern. And so once it starts with 0 experience and you give it that reward and you allow it to explore the space, eventually in a few minutes, it begins to learn to move along that treadmill. So this is a pretty cool application. This one's done at USC, and they've done really remarkable work with this. So this could be extended to robotic devices or assistive devices. Over time, it can adapt to users as well. What is deep learning? So I drew it on the board why deep learning is important in comparison to machine learning here. But again, deep learning is a pattern recognition algorithm. It operates similar to your brain. So it has neurons, hidden layers. It's essentially like a simulated brain tissue. So here's just a cartoon on the left of what an artificial neural network looks like. And it's a very simplified version of how your brain works as well. So there's individual neurons that take in inputs and they go through nonlinear activation functions. And that interconnected web there gives you so many combinations that it honestly will find the best result that you couldn't even come up with on your own. It's super complex in all the combinations there. So, and you can see on the right, that's kind of like the corresponding biology where you have axons from each neuron entering into the next neuron through the dendrites. And so this was actually developed in the 50s or so, but the reason why it's really taking off recently is because as societies has walked forward in the amount of data that's been available, it's allowed neural networks to really improve their performance. And so that was kind of like the key ingredient that really helped deep learning in the past couple of years or decades, I would say. Oh, it's also really good for image recognition because as light hits your retina and it enters to the back of your brain through visual cortex. That process is very similar to how recurrent neural networks work, which is a type of deep learning. Yeah, so like I said, as it hits the visual cortex, it follows along interneurons here. And here's a good example of predicting what an image of a German Shepherd would look like. Here's a really good video example of how this works. Say you had an image and you input it into the model, it would make a prediction like a cat or a dog. And as you see the input here, you can see some of these neurons here lighting up more heavily than others. That corresponds to the amount of activation that neuron is being active. Activation is highly active there, essentially. But that shows that these combinations are important in the model when it goes into those nodes there. And so it's much like how when your brain forms habits, those neural pathways are more strong than others. That's the same idea here. It strengthens those connections there. And here's a visualization for the number of parameters. So each neuron has a weight and a bias associated to it. A weight is just the slope, and a bias is just your addition term, so shifting your activation function up and down. And this is important because all of these neurons have nonlinear activation functions, but they also have a lot of parameters. So as you grow the network, the number of parameters also increases too. So this is an example of there's this amount of layers and this amount of neurons per layer. And you can quickly see as you scale up, it gets very computationally expensive. So that could be a problem. So that last one has 34,690 parameters. So that's really why machine learning is important, because we can't think of all the rules for that many combinations just by ourselves. So this allows it to learn those combinations, finds the patterns. However, there's a trade-off between the size of your network and your accuracy. So although, like I was saying earlier, here in deep learning, as you can lift your performance with the amount of data on the x-axis, but then also the size of your neural network here. Sometimes the size isn't ideal for your kind of problem, right? So you don't want something too computationally expensive. So here's a nice figure of the trade-off between size and accuracy, where you have the diameter or the area of the circle being the number of operations that are performed in that neural network. And then on the y-axis, you have the accuracy on an image classification data set. And you can see here, there's some that are really just giant, over 155 million parameters and operations. It's kind of redundant and not needed, right? So if you had something that was a bit smaller, but even had more accuracy or comparable accuracy, you prefer that. So like the Inception one here looks to be really good. And yeah, for your task, you might only need a 70% accuracy. It depends on what you're trying to achieve, essentially. So that's kind of the main takeaway from this graph is there's always going to be a trade-off between size and accuracy. You're never going to get 100% accuracy if it's a very complex problem, but you also want to be mindful of the resources you have. You might not want to build such a giant neural network. So, I already talked about this on the board. So yeah, you lift your performance with medium and large neural networks. And this is scalable because of the amount of data that we've had in the past couple decades, and then the size of your neural networks as well. This is an important phrase called the bias variance trade-off. So when you're trying to predict a data set or fit to a data set, you have your observed data, but then if you are underfitting your model, it might not be good because If it's too simple, you might not be able to generalize onto unseen data, right? So the goal is to find a good fit, kind of like here in the middle, where you're able to fit to the data that you have while also not overfitting to the data. So right here on the right, you're overfitting this data here and you're including the noise in your data. That could be a problem. So if you were to take notes on this, because if it might be on your homework, you might want to write down that overfitting is bad because you're including the noise in your data. So. Then when you're looking at unseen data, right, you don't want that noise in your predictions. So here's a really cool example that I found called ProPlay AI. So they use markerless motion capture to look at a lot of parameters for pitching using just a smartphone device. And you can look at a lot of things like hip shoulder separation, trunk twist, shoulder adduction, knee flexion angles. And yeah, this is really cool in my opinion because you can get an athlete in their natural environment to do a particular task. And that way they're not changing how they move. When you bring them to the Auburn lab and you put on the motion capture markers, put on a wearable sensor, they move a little bit differently. So if you can capture in their real life environment, that's really, really useful. This is Nate Pearson from Toronto Blue Jays. He's a Major League Baseball pitcher. So here's him in his training facility performing a pitch. You can see things like shoulder elevation, knee flexion, external rotation. And he's used this in his training to do a couple practice throws and see how his mechanics are working. It's also useful because if an athlete is tired at all or fatigued, it might be useful to have something record your movements to see how fatigued you could be. Maybe your pitching speed isn't the same, or the way your arm length is reaching out might be a little bit different during maybe a different part of the season. So it's very useful for pro athletes, college athletes, things like that. Here's a really cool example called Thea Markerless. Because it can capture, people in their natural environment, has high accuracy, reliability. I had a demo with some of the people who founded the company, and it's really remarkable how accurate they did their predictions. So they validated their system just using cameras in an infrared based motion capture lab. So they have motion capture cameras around the room, like some of you saw at the Avi lab, as well as video cameras, and they recorded both of them simultaneously. And the amount of match that they found in the joint angles was pretty impressive, like within a degree errors. So there's some differences, like you probably talked in classes, the rotational angles differences. So like this is your joint and it's rotating this way. From your perspective, you might not be able to see as much. But if you're trying to figure out how someone moves on a different day, that could be useful, right? Even if there is some bias in the accuracy, if it's reliable and it's consistent on day to day, and you just want to see how someone's mechanics change from maybe a coaching strategy or something like that, it'd be very, very useful. All right. Here's another really cool pattern recognition example. So here's COAPT, their control system for the upper limb. They use pattern recognition, like I was saying. So the idea of this is, think of like a whole orchestra of instruments playing, right? Traditional standard control just uses one signal from a particular muscle at a time. So it's as if you're only hearing one instrument at a time and you can't hear the song in an orchestra. Whereas pattern recognition control, what it does is it allows you to listen to all the music of your muscles of your arm, for instance. And then you can be able to distinguish the song and the instrument. So this is a really good approach to showing how your motor coordination operates. And so, yeah, so you can see that different hand gestures from the wearable that they are attached here. It can control a prosthetic device pretty seamlessly too. It's pretty amazing, especially if you want to get the fine motor patterns of your digits. It's very useful to know the exact patterns that are occurring within that. You also have a simulation example down here. So seems like a very common approach when people are trying to build machine learning. Systems, they test on a simulation and then they apply it to a real world robotic device. All right, so we finished pretty much most of what we were talking about overall, but there are some important questions you should ask when you're approaching a problem, whether it's machine learning can be useful for that particular task. One question is, how good is it good enough? Are you aiming for high accuracy, high precision, or both? Kind of like in the Thea markerless example, you might be just looking at high precision. You just want, you might not be interested in accuracy, but if you're looking at a clinical application, that's really important. And you might want accuracy, right? The reason why the Thea markerless example did really well was they used a lot of data in their networks. Your CEO I was listening to said that they use 500,000 training examples. So they have images of 500,000 examples. And they had a whole team of people working 40 hours a week just labeling the images. And then once they increased that to 750,000 examples, they saw pretty good results. But then now they've had over 1 million different examples, and that's how they've gotten some state-of-the-art results. So it's kind of interesting to think that a lot of the power within deep learning is just more data, really. So one area is, how are we going to be able to label all of this data without a human? If a robot or a computer can do it for us, it could really accelerate the amount of performance that we are trying to achieve. It's pretty exciting. Another important question is, what is the processing time for your AI to make a decision? And does this fit within your time constraints of your application? Example is, if you have a self-driving car that has 100% classification accuracy to see a stop sign, but it takes 10 seconds, that's not a good thing. So you want your time constraints when you're deploying this out. We're working on exoskeleton right now. So if we have a really good prediction accuracy of the exoskeleton, that's one thing, but can you actually make that decision fast enough for the human to respond with the exoskeleton, right? These are really important questions to ask based on your application. And here's a very, very important point. A machine learning model is said to be good if it gains the ability to generalize on unseen data. If you train on a certain data set and cannot predict unseen data, you did not do good on your training. And that's because the goal is to deploy your models out to unseen data and use that. there's a lot of worry that people think robots and machine learning and AI might take over the world, but they usually do one particular task really well. So like it's called artificial narrow intelligence. So they're just doing one task really well. They are not really good at doing general activities. So like your self-driving car can't write a love letter to your girlfriend or something like that, right? So it's not artificial general intelligence, it's just main AI. But if you're able to generalize on the particular task you're doing, then that particular task, your model is doing really well. Yeah, here's a funny little cartoon. So a lot of people think if you just kind of pile in as much data as you can get your answers really quickly and accurately. But sometimes there's other methods that need to be addressed, not just the number of data, like I was saying here, but the type of data. So here, this is contingent upon, the performance is contingent upon the amount of data that you have, but also the type of data you have. You don't want to use EMG data to predict someone's age or something. Maybe you could, I don't know, but it depends on the application, right? So some other limitations and challenges. So things can fail silently. So there could be bias in your training data. So your model only works as good as your data that you give it. So an example of this is there was an AI that would predict someone's occupation given their age, their race, their height, gender, and they found that if the race was Black, it was more likely to predict that they were a drug dealer. So there's some implications where you don't want to have too much bias in your training data, or else there could be kind of bad consequences. Also in image recognition tasks, using cameras, sometimes the lighting isn't best for people with darker complexions. So make sure that you have a balanced data set there, so that way it's not biased toward a particular group of people. Data can be messy, like I was saying, garbage in, garbage out. So you want to be able to find data that's useful for your particular task. And then you can also try to figure out ways to maybe transform that data to make it look like the kind of predictions that you're going to be making in the real world. Quality of data, there could be outliers, there could be missing data. Another consideration is collecting training data. So it can be time consuming and resource intensive. So the example that was from Thea Markerless, although it was resource intensive because all of their employees were labeling data 40 hours a week, it was worth it for that particular application to improve performance. But it depends on your application. If time is a constraint, you might not want to collect all of your data. If you can find open source repositories, that's really useful too. And we'll show an example later too, because those data sets, they've already done the hard work. They've already collected the data for you, so might as well take advantage of that. So. The hardest challenge isn't choosing the machine learning model. A lot of times it's just finding the right path. So that's really important to know. Here's another limitation. My deep learning professor said, recommended that I put this in today's lecture. Here we have Moore's law. So every 2 years, it increases by 2x. In the gray, we have hardware computation. And that's measured, this is all measured in the y-axis in flops. That's just computation. Just think of it as computation. And then the x-axis, we have the year. So you can see there's generally this kind of steady growth here in the gray. Whereas a lot of the computer vision, natural language processing, speech recognition tasks are increasing 15x in their computing and need. So remember we saw the giant networks where it had like millions of operations. So the need is outpacing the availability of these hardware here. So that's a really big problem. And then you can see more recently transformers, which use self-attention and vision tasks. They're increasing by 750x. So there's a big need for hardware computation to catch up, or maybe software slows down, but I'd rather see the gray increase at a more rapid rate. So here's some tools and resources that you can use for your future here. So you can use Google Colab. So this uses Python. It's at colab.google.com. And you can get started right away. You can use their GPU and you can rent out their TPU, tensor processing unit. So it's fast computation for free. And Python has really good machine learning libraries too. But most of you are familiar with MATLAB. If you have good programming skills with MATLAB, Python is probably easier to learn. You can pick it up really quickly. There's a lot of courses you could take. And the libraries through scikit-learn is really powerful in Python. So it might be something to consider. But if you want to stick with MATLAB, they have some toolboxes for machine learning that you can use. It depends on what you are at your stage of life. So most of you are seniors. So maybe when you graduate, you might not have access to MATLAB licensing. It'd be costly. So if you wanted to start your own business, maybe you wanted to do a free option like Python. So like I was saying earlier, data to train and test models. Since you might not want to collect all your data, you can look at open source repositories. So Aware is open source wearables. And visualizing model architecture, there's a nice little playground that you could play around with called Neural Network Playground that you can go onto and see the differences throughout there. We got some time, so I guess I'll just go there. So here you can see some inputs, and you can increase the number of neurons. You can look at a different data set to predict, like these clusters here. So like, for instance, here you have these two clusters. Maybe you only want 2 neurons here with a linear activation function. And then when you hit play, you can separate that pretty well. This is a linear approach. But if you were to maybe change your data to something more complex, it's unable to fit that nonlinear spin there, but maybe you might want to add neurons, maybe change the activation function to nonlinear, like remove. See, there you go. So this is a fun little playground you could play with. That way you could see like what size of architecture you might want, what kind of activation functions you might need, and if you don't know all the terms here, Google's a great resource. So yeah. Moving on, so a nice self tool is a machine learning roadmap. I recommend this one by Daniel Bork. It's really nice because you could start anywhere. So if you have 0 experience, even in math or statistics, they have a roadmap for you. But a lot of you guys are really intelligent engineers, and you have really good math background. So and some of you have pretty decent coding background. So this would be a great step for you to jump in and try some of their tutorials out through this roadmap. I've been following some of this for the past year or so, and it's been very helpful. All right, so Aware, like I was saying earlier, this is the open source wearables. There's a lot of data sets, algorithms that are available. They have wearable sensor data associated with it. This is your homework question, by the way. So we're going to ask you to go to the data set. You're going to choose a data set that you find interesting, and then you're going to describe the type of problem you want to solve. So if it's an injury risk or rehabilitation monitoring. So I can just show you right now what it looks like. So you're going to have a link to the website. You'll have a link to this website here directly. So you don't have to click those past 2 clicks there. So here's a nice little spreadsheet of all of these data sets that have already been collected, which is really, really nice in my opinion, because there's so many hours that have been taken into this. Our data collection has taken over 200 hours of just collecting data from people. Some people in this room were test participants, you know how long that takes just for your single session, but we had so many different subjects come in. So anyways, so an example of what you want to do for your homework, you would choose any kind of data set. So for instance, I'm not sure, can everyone see from here? Oh.
Can you make sure that you're sharing that so that I don't remember if I shared just PowerPoint or that for the screen.
Let's see. What I do, new share?
Yeah, try that.
Okay, good catch. They didn't see the neural net playground. Oh well, they can go there themselves. All right, so here you can see different data sets. So this example is activity recognition with healthy older adults using batteryless wearable sensor data using an accelerometer. So an example would be, I want to do a classification problem using this data set to predict these types of movements. Someone walking on a chair, sitting on a chair, getting off the chair, walking to bed, lying on the bed. And I find this problem interesting because maybe an elderly person might need assistance without 24/7 care. I don't know, something like that, right? Another example would be EMG data for gestures. So you have EMG data, and maybe you want to predict a hand gesture movement using EMG data. So this would be a classification problem, right? So you have your hand gesture, so maybe like a power grasp versus a button press. I don't know. So think of some ways you might approach a problem, but you can explore all these data sets and find one that you find interesting. The goal of today's lecture was you able to look at certain problems or data sets and recognize what kind of machine learning task would be applied to that. So hopefully the answers on your homework will be indicative of how well I communicated that. Yeah, be creative. You can share, your own startup company name, use puns, that'd be funny. But anyways.
Just move it to your screen.
Yeah. Good. All right, moving along. Okay. Does that make sense for the homework problem? Any questions with that? Pretty straightforward. If you have any questions, just email me, and then I can hopefully help you guys figure out what you need to do. So. All right, so today we covered what machine learning is. We covered supervised learning, unsupervised learning, transfer learning, reinforcement learning, and deep learning. It's a lot, but these are the main types of models you'll see as you graduate. You'll see more and more of this in your job industry. We looked at machine learning examples in biomechanics, specifically why biomechanics is particularly a useful field to apply machine learning due to the pervasiveness of wearable sensors and how complex the body is, right? And we also discussed limitations and challenges, and then tools and resources. So feel free to use those tools and resources for recording this lecture, and we're also going to post it on Canvas, so you can always go back and play through that. Some ways to stay connected: we have the Avi Lab Instagram, and also connect with me on LinkedIn. I post some of our approved conference stuff there. So, yeah. Good luck with everyone on their final semester if they're a senior, and hopefully from today I was able to maybe set a seed of interest for you guys to maybe apply machine learning to your problem, or maybe to avoid it if you didn't like today's lecture. But yeah, hopefully today you'll be able to recognize what that looks like and then how you can apply it for your research. Any questions?
One thing you were mentioning in there about the neural networks was the type of activation of the neuron, whether it was like linear or not. And I know that you went through something called like ReLU. What does that actually help with? Does it help it look at different patterns in data?
Yeah, great question. So the different activation functions in the neurons essentially determine the shape of how those inputs will be passed through the function. So ReLU is a really good one called, it's short for rectified linear unit. And so it goes kind of like flat, and then it goes as a combination of linear this way, and then flat this way, so it's a nonlinear pattern there. And so as it passes through that, it's able to learn more of the nonlinear mappings between some of the inputs to outputs. So, yeah, there's some really good resources on the visualization of them. I might have included it. Yeah, this one here, neural network from scratch.io and NFS.io. Yeah, that's some of the videos I was showing with the architecture. So they show you how it changes between linear versus nonlinear activation functions. So yeah.
Thank you.
Yeah. Any other questions? We have about 10 minutes or so. Thanks guys for coming in this rain.
Sure, David's willing to hang out for the last bit of time we have. Hand back the rest of these exams. I did want to say that for your own interest, double check. We tallied up, so I graded all of them, and then David and Sierra tallied up and input your scores. Okay, so like David was asking me, Sierra was asking me this morning if my 4 was a 9. It was 4. Okay. So please double check. I'm going to post the solutions probably fairly soon in the next couple days. So if you got any questions, you're welcome to come in and talk to me about it. All right. You take off if you don't want to hang around. Otherwise, I'm just going to start calling names and we'll go for about 10 minutes. Francis Cheshire. Chase Claiborne. Sean Parkins. Dominic Gibbs. Eric Pia. Kane Thompson. Jeff Gion. Brittany Rancy. Tyler Lindsay. Andrew Weir. Marshall Wu. Wait, you Ken. Sean O'Connor. Mary Margaret. Ryan Kelly. Logan Tilly. Julia Hancock. George Abraham. Harry Kane. Jackson Younger. Deontay Ryu. Neil McMillan. Wesley Connor. William West.